is more challenging than it is. Well, that ends well. So I wanted to talk about, I wanted to start off by reviewing some things from Kevin's talk. So basic things, factorization. Here, recall. So our setup is the fact the personal x, the smooth proper curve. Properness here in everything I say will be really important. So let me emphasize that. So we have something called a Ron space. So the kind of object it is, this is a pre-stack. Now, a pre-stack is something that you can evaluate on affine schemes and get a groupoid at the end. Here it will be just a set. Now, the S points of this pre-stack is just non-empty finite subsets of X evaluated on the reduced part of X. So that's a perfectly fine, that's perfectly functorial in S. And so well, we have this and a somewhat non-trivial fact about this. So for the most part, this is the description that we want. But for technical reasons, it's convenient to recognize this as a colimit of pre-stacks. This is also a colimit over the category of finite sets and surjections, finite non-empty sets and surjections of powers of the curve. What's that? What's cute? So anyway, part of a fun exercise to identify those two, but anyway. It's rather formal, so for the most part, we'll be concerned with this description, other than to say, well, like this is finite type, so there's no issues of what kind of sheaf theory. We can consider, well, I don't know, we'll want to study D modules or equivalently quasi-coherent sheaves or equivalently incoherent sheaves on this thing. What have we been calling this something?
It was quasi-coherent.
Quasi-coherent. Okay. Yes. So this is a kind of the category where this is a category where factorization things will take place. And so what's the first important thing? So if you have some important features. Well, let me name them. So there are kind of two important features of this thing. One is that, well, we have this projection map from around X to a point. And that I upper star has a left adjoint. Little weird to help anyway. It's quasi-close pi upper star, and then you have the other two equivalent definitions of that category could be called pi upper shriek, but let me call the left adjoint pi lower shriek anyway. So it has a left adjoint, and the reason for this is essentially the fact that X is this is what properness of X is from this presentation. This is a colimit, so for each one of these, this is proof, and colimits preserve this kind of aspect. And the second feature of it is that the space, whatever this means, is contracting. And for the purposes of what did just say implies, it's actually contractible in a stronger sense, so we won't need it, which is that which is that the counit of this adjunction is an isomorph. In other words, if you pull back something from point and you integrate it, you get back to where you start, which is a feature of contractible space. So this is a very important aspect of the run space. Okay, good one. Has this come up yet?
Not the second part.
Okay, right. What's that?
So this.
Oh, well, you can ask for something stronger. For instance, you can realize it as a topological space and ask that that you. And this is true also. Like in particular, you can ask that if so this is about like homology is trivial. Like if a space is trivial, if pi1 is trivial and the homology is trivial. This is the statement that the homology is trivial. You can also ask that there not be any, for instance, local systems. That's true. There are not.
Like, can I ask an extremely stupid to make this picture? But you just read it in the module instead of selecting what's going to choose.
I'm happy to do that. I was. Okay, you can.
That's how it was introduced. We can change it.
Yeah, okay. So those are, because it's Durand, because it's its own Durand step. Those are the same categories. So. So sure. And then. Because in D modules, this category is called aperture. Durand preferences about right versus left.
No, the bottom thing. Yeah, they need technology.
What's that?
So you can just write that it's the homology of our state.
It's this thing? Oh. Well, really, it's something like compactly supported homology.
Of the dualizing.
It's homology.
Oh, homology, yes, I agree. Of the dualizing, yes.
The definition is that local systems are trivial cancels.
Yeah, for instance, yeah. I mean, they're various equivalent formulas. That's a perfectly good definition.
Just as a comment, because I know there's lots of there's sometimes people call this homologically contractible, the single condition, and it's just shortening it. But also in the other.
Well, no, I wrote an arrow. That's like.
Yeah. Okay. Fine. Yeah. Okay. Homologically contractible.
Yeah. I just want to use the word. That's not.
Also, the whole group.
Yeah. So.
But X should be connected.
Yes. This is thank you, sir. Sorry, I just got that. Pay zero. That's another obstruction to contractibility. Yes, indeed. Thanks. Okay, great. Great. So now, there's another feature of it. So there's wrong. I'm gonna drop the curve now. I think we've been doing that. This joint. Well, I'm just going to say this in words informally. It's those pairs of subsets whose graphs are disjoint. And the other structure that it has is that wrong is what's the word for a monoid without a unit? Semigroups? Is that the word? So there's an operation called union. Which just takes two non-empty finite subsets and concatenates. Okay, so then doing a factorization algebra. It's roughly the following thing. The following data. So the first piece of data is it's a D module in the run space. In other words, well, in terms of this description, it's like it's a demodule every power of the curve compatible with diagonal. So that if you restrict along any diagonal map, you get kind of the smaller one. And the second thing is what's called the factorization condition. Factorization data. Isomorphisms. Well, it looks like this. And if you take the box product, if you take A, it's here. Take if you restrict it along this union map, and you restrict it to the disjoint part, you are given the isomorphism of events of product, but it's all also restricted to the disjoint. So you should think that in some sense, like the fibers at any point are determined by what it does on single consent. So if you want to know the fiber at like a two point element, then it's just the tensor product of the two. The kind of interesting additional structure is what happens when the points move around and collide. Plus by our coherence, so it's the right fluid part. So these isomorphisms come with coherence. So for instance, for three things, there's a co-cycle homology. And since we're in the world of infinity categories, this amounts to infinite amount of data. But this is not a workshop about how to package that kind of data. Okay. So that's what I've this is a little bit of a review from Kevin's talk. It's only questions about. So I mean, roughly, you should have the picture that was drawn before. Maybe there are 2 points x and y. Here's kind of ax and ay, and the way that this is an algebra is maybe these points collide in some other point, and then what happens at the collision encodes the multiplication.
Is it correct? The factorization algebras are commutative algebras in some tensor category. Is it correct that they're commutative algebras?
Modulo. Well, so first of all, it's the there you can build a symmetric monoidal category as is such that factorization algebras are a subcategory of commutative algebras in that. Yeah, I'm not sure that's a particularly helpful point of view. I mean, I don't know. One should like a topological version of this, since we're working in kind of topological dimension 2, is the notion of E2 algebra. So you should think that they sort of behave kind of like E2 algebras. And whatever, it's a very natural question that whatever kind of construction you have for E2 algebras, to try to see whether there's what the version what it does in the world of more general factorization algebras and vice versa. You know, if you're into that kind of thing, a good exercise to do is whatever I tell you about factorization, more general factorization algebras, to think about the case of what happens with E2 algebras, or even sometimes E1 algebras. That's often already an interesting example. But anyway, I'm not, for lack of time, I'm not going to say much about that, at least officially. Okay, so now the definition. Maybe a factorization algorithm. Factorization. AKA chiral homology of A. Is just give it some notation. So chains, factorization chains, that's A. So this is defined as this left adjoint on the Ron space applied to that kind of underlying maybe let me give it. Let me give it a name to the underlying D module. In particular, a funny feature about this definition is that it actually doesn't use any of the factorization isomorphism in the definition. It's a thing that makes sense for any D module in the Ron space, and that will sometimes be useful. Sometimes we'll like the factorization does a lot, it implies a lot of good properties about this construction. But this kind of thing would have made sense more generally. Okay, so this is the definition. But to make sense of this, let me do a few examples. Or rather, so the first example is if A is what's called a commutative factorization of one. So this is
You write slightly larger.
oh yes. So Kevin explained that if I have just a commutative algebra in D modules on X, there's a functor, if it was given a name called FA for factorization algebra, that produces a factorization algebra. So you haven't different of X. So this is the category factorization algebras. So Kevin gave a geometric construction. When at least when A is connected, you take the spectrum of A. That's some kind of a D scheme over X. And then there was a way of producing a factorization algebra by looking at sections over formal disks, parameterized formal disks. So I'm going to. So for the moment, I want to black box this construction to just tell you the answer. That to be explained. A very important fact, which is that so let's say suppose so is what A is a commutative factorization algebra. So for now, it means it comes via this construction. Then this factorization homology of A, it has an additional structure. It's not a rank, so because this was commutative, this has the structure of a commutative algebra. So commutative algebra. And I don't know, so the spectrum of it, we'll say geometrically maybe. And I'll say it more algebraically. This is the, well, I think everything here is by default derived, but let me emphasize that. Anyway, space of horizontal sections of spec A living over X. So spec A over X is an affine scheme together with a connection. So we can look at the scheme of sections which are horizontal with respect to that connection, and the assertion is that this is the spectrum of the chiral homology, of the corresponding commutative factorization algebra. And so equivalently, and reformulate this. What this means is that maps this factorization. This is identified with maps in commutative algebras in D modules. What's that? Yes, thank you. Into some random commutative algebra. So this is in commutative algebras. So this is the same as maps of commutative algebras in D modules from this A into B tensor the dualizing complex. So if you have a commutative algebra, there's a way to produce a commutative algebra in D modules, just pulling back. And so in other words, this factorization homology in terms of categories of commutative algebras is the left adjoint to this pullback. So let me remind you in general, if you have a symmetric monoidal functor, the left adjoint won't preserve any kind of algebras, but there is a separate left adjoint, there's a different a priori mysterious left adjoint defined on, say, commutative algebras, and this gives a kind of an explicit way of evaluating that in this case. Oh, all right. I'll to right here. Okay, so that's what I wanted to say about the answer to this example, and a little bit later I'll explain a little bit about why this is true.
And maybe just to give a feeling, like, for why you say derived space the horizontal section, maybe you want to give an example of like how cross a line.
Sorry, why H1 appears or something?
Yeah. In the case of well, just that if you did this in the cases of like loops, like jets or whatever it's called into A1.
Yeah, fine. So example A is we haven't defined jets, and so I'm
Then you can do no checks if it comes to groups too many.
sure. Yeah, sure. So I'll take A to be O tensor A joint T. This is constant scheme. Spans A1 over X. And in this case, so what is this then? Then let's compute this, the chiral homology of this thing. That's A. This is going to be, well, the symmetric algebra on the Durand homology of X. Just applying. What's that?
The space itself is the Durand homology.
Space itself.
Like you expect of trying to say on the top line, you expect the factorization homology, and what you're gonna get is like the derived scheme of this Durand homology.
Yeah, sorry, I said that what the algebra is.
Yeah.
Oh, so there's dual, I agree. Yeah. It's the anyway, yeah. So if you follow this through, so the reason you could know this is because this is the way this left adjoint works is it takes free algebras to free algebra. So this is the free commutative algebra on O. Therefore, whatever this will be the free commutative algebra on the left adjoint functor evaluated on that, which is exactly the dual of Durand homology. So,
Wait,
all right.
wait, you just spell out for people what is the connection between a horizontal, like just between that answer and just like literally a horizontal section of just like what projects.
Literally, a horizontal section is a map from that thing to O, which is horizontal, And so, which is the same thing as this, as a horizontal section of like the dualizing sheet. Yeah. All right. Any other questions, remarks, requests? Okay, great. I'm good. Okay, 3 minutes. Okay, so let me do the second example, which is Pat Moody. Moody. So we defined. So let me simplify things and say at level 0. Here, this doesn't really matter. And so we have this. Was this the thing that we, was this the name for the corresponding factorization algebra?
There's one different things. One was back of G.
Vac of G. Oops. Vac of G, this is the factorization algebra corresponding to that's movie. It appeared yesterday, and the assertion is that factorization homology G. Now we're going to see connections with Sam's talk. It's the Lie algebra homology of coherent homology of X with coefficient with this is more explicit. So take the coherent homology of X, tensor that with the Lie algebra. This is a commutative algebra. This is a Lie algebra. So the tensor product of a commutative algebra and a Lie algebra has a natural Lie bracket on it, and then takes Chevalier-Eilenberg chains on it. So I guess I'm not being careful about H's versus C's. Everything is chain level. Sorry about that. So the thing that I want to point out about this answer is that this is the kind of answer that showed up in Sam's talk for what the fibers of the localization functor were. This should remind, at least be reminiscent of what the fibers of the localization functor are. We'll say more about that shortly, and maybe I'll leave it as an exercise, which is to deduce two, that's this one in the abelian case. From 1. So the abelian case of this is actually a special case of that. In this case, this is a commutative factorization algebra.
And Nick, maybe you could write on the board to make a connection with my talk, but this is also that another exercise people can do is that this is the fiber of the sheet of differential operators.
So observation is if I take a G bundle, let me pick a trivial G bundle. Oh well. Let me pick a G bundle. Then if I take the sheaf of differential operators, what was the name you used, Fred?
I used like 8 different names.
All right, so okay, let me just call it diff, and it's differential. Too many, so it's otherwise it's going to be a tower of subsets. So the sheaf of differential operators on 1G, that it's fiber at P. This is there's an isomorphism between this and something very similar to this, except instead of the tensor product, I take the Lie algebra and I twist it by the bundle, where I use the adjunct action on the Lie algebra. So this is still a sheaf of Lie algebras. Its homology is a Lie algebra, and I can take Chevalier-Eilenberg chains. So this has this kind of nice description. Yeah, does that satisfy your question, Sam? Okay, great. Yeah. Yeah, this is sort of a starting point for describing this localization function in factorization terms. Is this observation? Okay, maybe I'm supposed to stop for a break, so let me do that now. I'm behind schedule, but I think it's okay.
Are you done with factorization or with factorization algorithms? There's homology.
For the time being, yeah.
If I want to.
So the next is so after the break,
Yeah.
I will start talking about units.
Oh, okay, that's perfect. Yeah. So that's what I meant. So like.
But then I will come back to this.
Yeah. But so. Right.
Yes.
So this unit is finished.
Yes.
And then we put units.
Indeed. The pre-unit unit is complete.
That's